correspondent. So I'm here this morning to try to address your question about what electronic engineering is and what it means for you to study this major in the university. Please come in. There will be a 10-minute session in the afternoon. If you're not listening very well this morning, you're welcome to attend the session as well. I'll try to make this informal and give you an opportunity to ask me any questions that you may have. So, electronic computer engineering, your future begins here. In fact, the future is here in electronic engineering. I can say that because I can say that electronic engineering is really the only discipline in engineering that I can claim that we create a future. I know the future begins here because if you look at today, which was yesterday's future, we created today. So we know that we continue to create a future. I will come back to this slide later. So what is electronic engineering? Electronic engineering is about the creation of everything that makes the modern world. The LED lighting and display, this monitor, the projector, the touch screen on your cell phone, your smartphone, and all the sensors that come along with it. You may have seen drones and self-driving cars. Some of you may have signed up for the self-driving car workshop. You hear a lot about AI, artificial intelligence, autonomous vehicles. It will soon become reality. We don't have to drive anymore. The cars will drive them where we need to go to. And then there are also a lot of things behind the scenes that we may not directly touch or see, like the cow server farm. The fact that you can go online, search for anything you need to, all these video being streamed to us. Because of all these very large server farms containing hundreds of thousands to millions of computer servers that perform all the AI calculations, performing all the searches and data storage and so on. And then behind that, there's a global communication network that connects everything together. Since about 40 years ago, I started working on this. So anybody know what this is? Anyone? This looks like a string of wire. Yeah. Any guess? Shield some ice, shield there. Well, this is a very inexpensive optical fiber. Actually, it's glass. This is ceramic glass. This is a very inexpensive fiber used for connecting servers inside the server farm. So we first had this 50 years ago, 1957. The rate at which we can send data through this cable like this, double every less than 2 years. In the year 2000, I worked in the industry for a long time before I came to the university. And in the year 2000, in the backbone of the network, we have fiber that are able to transmit information using many, many colors of light simultaneously. Transmitting information at 160 gigabit per second. And then for desktop, among the server, using the inexpensive fiber, we just arrived at the rate of 1 gigabit per second. So 1 gigabit Ethernet, that was the speed. So it's this piece of cable, but using glass fiber. Well, today, you guess what's the speed of Ethernet that we have connecting this server, the server farm? Take a guess. Today. So year 2000, 23 years ago, it was 1 gigabit per second, 1 billion bits per second. today? Yeah, about right. It's 1.6 terabit per second. So 1,600 times in 23 years. 3.2 terabit system is coming to the market. So that's how we can do all this AI, and we can transfer this data so quickly among the computers. And the technologies and all the innovations we apply to make that possible has been simply amazing. So, what do electronic engineers do? Well, this is such a broad subject. We do so many things. I cannot possibly completely describe it, all that we do in one morning. But very generally, we say that we do 3 levels of things. First, we create smart devices, and then we use these smart devices to build systems, and then from the systems, we connect all these systems together to connect the entire world. So at very high level, this is what we do. So electronic engineers are explorers. We explore what are possible. We are innovators. Innovation means applying technology for useful purposes. And we also problem solvers, solving problems. So first, we create smart devices. Well, there are many smart devices. One thing that really launched today's information technology revolution is the transistor. Anybody heard of transistor? What does it do? What does a transistor do? Does anybody know? Any student? Nobody knows. Well, a transistor is simply a tiny device that switches current on and off. You just turn the electric current on, off, on, off, on, off, on, off. So why do you want to turn current on and off? Well, that is the language of the computer. Now, when we write human being, we use letter. We use A, B, C, D, E, F, G, and 1, 2, 3, 4, 5. But for a computer, everything is translated into a binary language. So for a computer, the language only contains 2 letters, 0 and 1, or current on and off. So using a large number of 0 and 1, for example, the letter A, I can translate it into a binary language, making up of 0, 0, 0, 0, 0, 0, 1. And now B would be 0, 0, 0, 0, 0, 0, 1, 0. So I use a different strings of 0 and 1 to represent A and B. So the 0 and 1 is the language of the computer. And a transistor is a very small device that turns current on and off to represent 0 and 1. So the transistor was invented in 1947 at Bell Lab in the United States. In fact, that was where I worked after I completed my PhD. So the transistor was invented right there. And the transistor is what made the modern information technology world possible. Prior to that, we did not have any efficient way of manipulating electricity. So the modern information world is all about manipulation of electricity. And we also build other devices as well, amplifiers to amplify signals, modulators that vary signals for communications, LEDs, light emitting diodes for both lighting and also for display, solar cells for converting sun energies into our useful energies, and also various types of sensors for camera and so on. One of our colleagues had a very noteworthy innovation, which was an artificial eye that will be, in the future, will be able to help people see. Of course, there's the optical fiber and also the transmitter modulator needed to manipulate the light signal, the optical signal for transmission over the fiber. And then we build efficient systems, meaning that we connect many devices together. Integrated circuits, I'm sure all of you have heard of this word, chips. So chip is a very tiny device today containing billions of transistors. At least hundreds of million transistors to tens of billions. And for some chips, like GPU chips, I'm sure some of you have heard of, graphic processing unit chip, can contain trillions of transistors. In 1959, we built an integrated circuit with only one transistor, 1959. Today, we build integrated circuit containing a CPU, for example, would be tens of billions of transistors. And then with the integrated circuit, we build smartphones, computers, telecom equipment. I spent the longest span of my career working on telecom equipment, robots, and drones. Then we connect the world. The Wi-Fi that is working in this room, the 5G network that is already deployed today, the 6G network that we are working on, fiber networks that I have worked on for 40 years, satellites, and also Internet of Things. Well, in fact, in my first year of college, I was actually a civil engineering student because I like to build large things. And then somewhere along the line, I saw one of the laboratories had a satellite. I was really fascinated by that. So I talked to the professor, and I get work on the project related to satellite, and then I transfer over to electronic engineering. But what makes electronic engineering different from other disciplines of engineering? So I hope this is a key message that you will take away with you. What would you say? So to you, how is electronic engineering different from other disciplines of engineering?
Very small. Very small.
Very small. Okay. That's what I thought when I was a secondary school student. So I didn't like it that much. I have never came to be an electronic engineer because I like to work on big things. So I did not like to sit on a desk and then doing soldering and components. That was not quite me. So that's what I thought. Yes, some of us work on things that are very small, but many of us work on things that are very large. In fact, I found my calling because when I built this network, they span the entire country and they span the entire world, having hundreds of nodes and hundreds of millions of US dollars, very large networks. So some of us work on things that are very small, but some of us work on things that are very, very large. Any other answer? We in fact my answer now, I'll give some hint. In fact, electronic engineering is a broad discipline in engineering. It's very, very broad. I cannot really describe it in one morning what it entails because it entails everything. Why is electronic engineering the broadest discipline in engineering? Well, that is because the science that we are based on in electronic engineering is the most fundamental, one of the most fundamental sciences in nature. I can say it's the most fundamental science. I'm sure many of you study physics. So in physics, what do you study?
Mechanics.
Mechanics, okay. So after mechanics,
Big bang theory.
Big bang.
Big bang theory about space.
Space, okay, right. So the relativity, okay. So there's the Newton's mechanics, and then you maybe study some heat transfer, right? Some heat, maybe, well, not yet fluid in high school, but that would be relativity. Well, certainly then the electricity, right? Next would be electricity. So in the 17th century, Isaac Newton, famous mechanic, so he introduced a concept of force and motion, force equal to mass times acceleration, and so on. So the world works in a very mechanical way. But then there remained this mysterious force, electricity, that people observed in nature, but people did not know what it was. So we found static electricity, we saw lightning, we saw animal electrical, and also we saw observed magnetism, we saw magnet, but we did not know what it was until the 19th century. So the year 1800, the first battery was created by an Italian scientist by the name of Sandro Mota. He created the first battery that is capable of generating a constant source of electricity, so a scientist can do experiment, perform experiment on electricity. And then there was one famous scientist, British scientist, by the name of Michael Faraday. So, anyone heard of Faraday? So Faraday, yeah, about the electricity, right-hand laws, and how electricity is connected to magnetism. So, from then on, from the 18th century, our science is really all about electrical science. It's about the understanding of electricity. It's the understanding of electricity that brings the modern world. So Faraday's discovery led to the telegraph and the telephone. The telegraph in 1830. You don't know what the telegraph is now, but the telegraph is like the internet of its day. Before the telegraph, there was really no market. So the telegraph enabled commerce and market. Now before the telegraph, there was trade. There was maybe a market trade where people sell the food and grains and so on. But there was really no market because there's no information flow. The producer of cotton in the United States has no idea what the demand would be for cotton in England. So there's really no market. So electrical science enabled commerce. So since the 19th century, our most fundamental science is really all about electrical science. And also the method we use for understanding electrical systems are fundamental to understanding of all systems. And we have the most subspecialty. I can even list them all. The work of an electronic engineer may range from basic science, so something very related to asking fundamental questions about science, to applications in making circuits and computing systems. It can be very theoretical, ideas and concepts and algorithms for control and communication, and also for artificial intelligence and data analytics. It can range from hardware to software. You can be building circuit, doing soldering, something very small, or you just sit in front of a terminal and just do programming. You can work in a lab, sending signal through this fiber, or you can just stay in your office, writing simulator. You can work on things very hands-on or purely abstract. And then you can work on things that are of very, very small, nano scale, to very, very large, mega scale. So what do we study in electronic engineering at HKUST? Well, we study a basic science. There's some basic science and basic math that are very fundamental that you can use in many disciplines of engineering as well as in business and other disciplines. So we study basic science, the modeling, the mathematical techniques, and the design principles for creating smart devices, building efficient systems, and connecting the world. So first, we need to understand the basic science so that we can understand things in a very fundamental way. We also need to learn all the techniques we need to modeling things from nanoscale to megascale. Then we can, through design, connecting these devices together to make various types of systems, and then we can connect them together to connect the world. So our curriculum at a very high level, first you need to study some basic math and science. So for science, mainly it is physics, the mechanics and electromagnetism that is required for electronic engineers. Basic math would be calculus and another choice of differential equation, linear algebra, probability, and multidimensional calculus. So these are very general math techniques. In fact, throughout my career, I found that the most basic math and most basic science are the ones that are the knowledge that would remain relevant and stay useful for a longer period of time. Because the world is changing so fast, everything we learn at the application level changes 10 years later. It is the fundamental things that would be the most relevant throughout your life. We also study some overview courses that will give you an overview of what an electronic system is and what a communication system is. So this gives you an overview of two of the major disciplines in the so-called infotech or IT. So information technology is made up of two main aspects. One aspect is computing. The other aspect is communication. So this is an overview of computing and communication. And then you learn the basic modeling and analysis techniques. And two courses on hardware and software design and implementation. After that, so we only have a very small core courses. So this is a very small core. Compared to another program such as computer engineering, they will have a larger set of required courses, covering both software and hardware. But in electronic engineering, we have a smaller core, and it will give you a greater flexibility to choose what you like to study. After these core courses, then you can choose whatever courses you like to study in a very large variety of specialty areas, including photonics, microelectronics, IC design, control system robotics, signal processing, communications and networks, data science and AI, biomedical engineering, and so on. So you can choose to sample many specialty areas, or you can stay focused in one very specialized area. The choice is up to you. At the university is the time for you to discover your interest, your calling, your aptitude, and decide what you like to do, what you like to pursue in your life. Many subjects in the world today are very fast changing and are increasingly multidisciplinary. So there is not one single formula for every student. In fact, every one of you are different. You are individuals. You have to chart your own course and your own combination of skills. Our electronic engineering program intends to train you to become leaders in addressing the world's new technology and business problems. You develop according to your aspiration and your skill. You are not a commodity. Students are not commodities. They are not all the same. So at EC, you have world of choices and a world of opportunities. It is very important. I advise all my students. I'm responsible for undergraduate education. I encourage all my students to discover the interest and then make their choices. Our life is the result of a sequence of all the choices that we have made. So we have made. So good choices, good life. So we need to make good choices and make informed choices. You should ask yourself a number of questions. What type of job nature do I want to be involved in? Am I a scientific person? Do I have a scientific curiosity to understand nature? Or you can be a technical person. You want to make things that work. You find a lot of satisfaction building things that work and can be used in the world. I have found a lot of satisfaction making optical communication systems that work. When I send data into the network at one end of the world, and after all this complicated processing, and I see the data coming out on the other side, I found tremendous satisfaction. So maybe your interest is to make things work. Now some of you may have interest in being managerial. You want to make advancement in your career, be in a senior position, leading others, driving changes. So that's managerial. Or maybe your interest in business, you enjoy making money. Well, there's nothing wrong about that, because that's what drives our modern economy. So you can be involved in money-making part of business, like marketing and sales. In fact, for several years, I did marketing and sales. First, I was an engineer, and then I sold telecom systems. And then some of you want to create new business. So entrepreneurial, like start your own business. So you have to think about what excites you the most, and then you choose a job nature. And also, you need to choose what industry that you may want to be in. What type of industry interests you? There are electronic engineers are involved in many industries, but at a high level, I kind of categorize the choices for our students into these major ones: software and ICT, infotech, electronic designs and electronic systems, including circuit boards, computing system, robot, things like that. So that's for students who are interested in hardware and electronic components. Telecom and networking, this is a very large area. I spent most of my career in telecom and networking. Semiconductor and IC design. Some of you may want to pursue a career in a large, stable company or work for the government. You may want to work for MTR, China Light and Power, or Hong Kong government, these large companies that provide stable employment. Or many of our students also go into consulting, banking, and finance. For example, I have advised several of my students to go to accounting firms. Because many accounting firms actually hire technical consultants to help the client to accomplish various technical things. So it depends on what type of pay you want to achieve, what type of job that you want to have. You need to think about job nature and industry. So the future is here today in electronic engineering. On the left, can somebody tell me what you see on the left? What's on the left? Okay, chip fab. Very good. So this is a wafer. So this is a wafer. Wafer is a circular disc. Today is typically 12 inches in diameter. And that's how we make the chip IC. So we use a lithographic machine to actually print all the transistors and circuits on the surface of the wafer, layer by layer. So there may be anywhere 20 to 30 layers of transistor and circuits. So every tiny square here is a chip. So after we're done, we actually will slide this wafer into the individual chip, package it, and that is the IC. And each IC today can contain tens of billions of transistors. And that drives our modern world. The past 10, 15 years, the major revolution in IT, well, you hear a lot about AI today. But before AI, the revolution was in virtualization and cloud. Can someone explain what virtualization and cloud is? Well, in the past, we just have our own computer, right? So a computer is a computer. But in virtualization, we have a common pool of computer. And we can make it, and then we can create virtual computer on demand, on the fly. So that is virtualization and cloud. So we create a virtual computer for someone whenever you need it. There are many, many advantages to that, because then everyone can obtain the computing resource he or she needs on demand. And also, we do not have to build specialized computer. I don't have to worry about my application being or not being able to run on different types of computer, because all the computers are virtual, and I can make the computer behave like any computer. In fact, that was a very major revolution. So the past 10, 15 years is all about virtualization and cloud. So now, of course, we all know that we are undergoing the AI revolution. AI is becoming smarter and smarter. ChatGPT can write our term paper for us. It can actually write research proposal for us. So AI is becoming very, very smart. Medicine, for example, will soon be taken over by AI. So a lot of things that physicians do can be replaced by AI. Of course, physicians, they will have to do something else, right, at a higher level. So both of these are enabled by what electronic engineers do. We make AI and virtualization possible, because without the devices and our computing system, then there is no virtualization and no AI. If you study computer science, you will tend to look at AI as a black box. You will just assume there's an almighty computer there for you to do your programming on. They do not think as much. It's not that they completely don't think, but they will not think as much about what the constraints are, what the power consumption would be, and how we can implement the AI devices actually into our daily life. So they will look at AI as a black box. But as electronic engineers, we will consider what it takes to realize the AI, to bring AI into devices and into people's life. Well, what is on the right? Does anybody know what is this?
Is that called a cable?
Well, a lot of cable for sure. Lots and lots of cables. Well, a chip here contains tens of billions of transistors, tens of billions of bits. This machine contains only 53 bits. 53. But it's a humongous machine. It's the size of the room. So what is this? Well, this is a quantum computer. This is a quantum computer that operates on only 53 bits. But these 53 bits, they are not just bits. They are called qubits, quantum bits. So in a transistor, a bit is either a 0 or 1. The current is either on or off. But a quantum computer, each of the bits is both on and off at the same time. Well, that's very hard to understand. But that's what physics is. In physics, any particle can be in multiple states at the same time, 2 states at the same time. So this machine is 2 to the power 53 states at the same time. So when it does computing, it is looking at all the possible inputs at the same time. So the trick for us to use it to solve any problem is to design an algorithm so that eventually the correct answer will come out. Because this computer is looking at all the possible combination of input at the same time. And that's how we can make computing much, much faster than a classical computer. Now when this becomes mature, it will make AI look like a juvenile. So AI will just be a kindergarten kid in front of this machine. But that's how we make progress. We start from things that are very, very big, then eventually we have to conquer, and then maybe one day we can put it into a tiny chip like that. So we create the future. The future is electronic engineering. Again, I know because today, which was yesterday's future, was created here. So I'll stop here and let you ask. Oh, also, if you have any questions, if you'd like to email me to learn about electronic engineering, personally, you're welcome to send email. So this provides a link to my email address. I spent 20 years in the industry before I came to the university. And also, if you have, and then in the previous slide, in your general administrative question about what it takes, what's going to take to get in and so on, then you can send email to EEG help. Thank you very much for attending.